Laws of Logic Part 2. The Law of Bivalence. The law of bivalence, also known as the principle of bivalence, states that every declarative sentence that expresses a proposition, meaning it is truth apt, is a statement that can be true or false, has exactly only one value, with it being either true or false. Logics that use this principle are known as two-valued logic, or bivalent logic. While related, it is important to note that this principle isn't exactly the same as the law of excluded middle, which states that a proposition must be either true or false, as there can be forms of semantics of logic which may have the law of excluded middle, but not necessarily the law of bivalence, such as multi-valued logic, which I will discuss in a future video. Logically, it can be expressed as, for all of P and P, P or P, meaning in the set of all proposition P, for any given P, either P or not P is true. As noted, multi-valued logic is not bivalent logic, and other forms of logic such as temporal logic or fuzzy logic may not use the law of bivalence as well. This is because some propositions may not be able to be properly understood in classical logic. For example, consider an apple that is partially red and partially yellow. The proposition the apple is red is true, and the proposition the apple is yellow is also true. Yellow is not red, and so the proposition, the apple is red and not red, would violate the law of non-contradiction, which I discussed in Part 1 on the laws of logic, and if it violates the law of non-contradiction, it by extension violates the law of bivalence. Other forms of logic such as fuzzy logic allow a proposition to be partially true and partially false by using fuzzy sets, where something can be things like mostly true, partially true, or somewhat true. This is highly practical in machine sorting and machine decision making to determine to what degree truth conditions are being met. Law of double negation. The law of double negation, also known as the double negation rule, also known as double negation elimination, says that the negation of a proposition is logically equivalent to the proposition itself. It is important to note that not all logics use this rule. In intuitionistic logic, you cannot logically derive P from not P via double negation. This is because intuitionistic logic rejects the law of excluded middle, allowing it to be used in logical systems where truth values may be unknown, and therefore cannot be directly derived via the negation rule. Law of contraposition. Law of contraposition states that if a proposition P implies a proposition Q, then the negation of Q implies the negation of P. We can see this logically follows by example. If X is a square, then X has 4 sides. If X does not have 4 sides, then X is not a square. Since having 4 sides is a necessary condition for a square, if X fails to meet the condition, which is the negation of the consequent, Q, then it cannot be a square, which is the negation of the antecedent, P. In this example, X is a square, is the antecedent, and X has 4 sides, is the consequent. The negation of the consequent is X does not have 4 sides, and the negation of the antecedent is X is not a square. Thus the negation of the consequent implies negation of the antecedent. Law of simplification. The law of simplification, or just rule of simplification, is a valid rule of inference that states that for any conjunction, we can simply derive one of the conjuncts. Given P and Q, then we can simplify and derive P as true. Given P and Q, then we can simplify and derive Q as true. For example, a square has 4 sides and has 4 internal right angles. Therefore, P, a square has 4 sides, or therefore, Q, a square has 4 internal right angles, as both the atomic propositions, which is the proposition P and the proposition Q, in the conditional P implies Q are both true. The law of absorption. The law of absorption, which is a valid rule of inference, states that if P implies Q, then P implies P and Q. This is often used in logical proofs when you want to rewrite the conditional implication meaning P implies Q, as a conjunction, which would be P and Q. Example, if a square implies having 4 sides, then if something is a square, then it is a square and has 4 sides. DeMorgans laws. These very important rules in logic, named after Augustus de Morgan, allow us to logically negate conjunctions and disjunctions. These laws state that the negation of the conjunction of P and Q is logically equivalent to the disjunction of not P and not Q, and that the negation of the disjunction of P or Q is logically equivalent to the conjunction of not P and not Q. Let's see by example how this works. Suppose again, we have an object where P means it has 4 equal sides, and Q means it has 4 internal right angles. Given that this is a trapezoid, it does not have 4 equal sides, and does not have 4 internal right angles. We can write it as not P or not Q, meaning that it has neither 4 equal sides, nor 4 internal right angles. Since a trapezoid cannot have both properties of having 4 equal sides and 4 internal angles simultaneously, we can use one of the DeMorgans rules to say it is logically equivalent as a disjunction, stated as not P or not Q, as at least one of the disjunctions must be false. It is of interest to note that there are many ways to express DeMorgans laws, as they are used in multiple different forms of mathematics such as set notation, Boolean logic, and electrical theory. If you would like a challenge, I have provided a link in the video description to a natural logic checker where you can prove DeMorgans rules are valid logical rules of inferences, using some of the rules I have discussed in this video, as DeMorgans rules may not intuitively be obvious to some. I have included the justifications required to have the proof pass validity check. Credit to Mathematics Stack Exchange. I have also included a link to a free and very helpful guide to logic using the natural logic checker called For All X, Calgary, which covers the truth functional logic, truth tables, syntax of first-order predicate logic, and justifications for the natural logic checker provided in the video description. I highly recommend it to anyone wanting to learn about formal logic, as it is excellently written, and while some of it, such as possible world semantics, can be a bit difficult read, much of the basics of formal logic are very well explained and easy to understand. If you like this video, or hopefully at least learned something new, please give it a thumbs up, and don't forget to like and subscribe. Feel free to ask me questions in the comments section, or just let me know what you think in general. Thank you for watching.